Okay, welcome everyone and everyone yet to arrive. Um, so today we're going to be embarking on a new module of the course, one that's going to be focused on uncertainty and agent-based and hybrid modeling. I'm going to make some initial remarks in this regard. But then we'll dive into one specific type of uncertainty, uncertainty associated with stochastics in a model. And we'll then be continuing on next time to talk about parameter-related uncertainty. And along the way, we will further discuss some uncertainty associated with model structure. This topic will bring us to the point where we'll also be speaking about ways to help leverage broader sets of data to manage that uncertainty through a process commonly known as calibration or parameter estimation, more bluntly. So this module is expected to last for several successive sessions, with today being the one that sort of kicks us off. So to that end, and I apologize, these slides aren't shared yet. I will seek to do so right after class. But we're going to, well, first sort of kick off this general topic with a few confined remarks, and then we'll jump into a discussion of the first particular topic on stochastic induced uncertainty in model outputs. So when it comes to thinking about uncertainty and dynamic models and agent-based models in particular, we're dealing with a quite broad topic that can be fruitfully approached in a number of different ways. And over the years, my group here at University of Saskatchewan, in our work both here and with collaborators worldwide, has embarked on a number of lines of research which have sought to approach the issue of uncertainty, grapple with it from different perspectives. Some of those are shown here, or are gestured at here. As time allows in this course, I'll take up some additional lenses, such as combinations of sensitivity analysis and calibration, sort of jointly conducted, such as bringing together machine learning techniques with dynamic modeling, including ABM, during the final lectures of this course. But before that, we have a lot of basics to cover. And I think one could do worse than to approach it from a standpoint that highlights a number of types of uncertainty given in this slide. These include uncertainty in model results and uncertainty about model results, including the impact of policies and more subtly the relative impact of policies or interventions. From the standpoint of stochastic variability, cases where model stochastics, randomness over time in the model, reflecting, say, noise or uncertainty associated with human behavior, associated with things like weather, economic conditions, etc., induce uncertainty in model outcomes. We'll be diving into that today in spades, and I'm not going to expand on it more at the moment. Another topic broadly explored in dynamic modeling, arguably disproportionately, but certainly approached in a number of different ways, concerns parameter uncertainty. Uncertainty regarding parameters, the value of parameters, can ripple through to uncertainty in induced model behavior. If we're uncertain about the contact rate between individuals or the rate at which they will take up a product, that can induce uncertainty on model outcomes. And we will be approaching this issue next time with an examination of parameter variation experiments, where we systematically vary a parameter, either via parameter sweeps, systematically sweeping through a bunch of different values, or drawing values for it stochastically or randomly from distributions, what's called Monte Carlo analysis. We'll examine how we can characterize outcomes of models, how outcomes of models are affected by or are more or less contingent upon assumptions for parameters. We'll also talk about calibration. Here, point estimating parameter values. By matching against data from the world, it doesn't relate to any one parameter of the model, but rather to emergent behavior of the model. And we'll be adjusting parameter values or parameter assumptions in the model such that the model's emergent behavior best matches emergent behavior from the world. That's quite different from parameter estimation, where we take some data from the world and we perhaps undergoing some backing out calculations or boiling it down in some particular way, combining it with some other data, we arrive at a parameter estimate. That's part of what is termed parameter estimation in a classic sense. But here in calibration, we're talking about taking data from the world that does not, again, relate to any one parameter, but is an emergent property of the world, and holding the model true to that, seeking to adjust parameter assumptions in the model about less well-known quantities, or assumptions concerning the values of less well-known quantities, so that the model output best matches that from the world. We'll talk some about structural uncertainty, how our assumptions about the structure of a model, whether we represent asymptomatics individuals in the world, whether we characterize there as being a latently infected stage of infection, whether we assume people lose immunity over time, etc. Are there asymptomatic infectives circulating? Structural uncertainty, uncertainty about the structure. Think like the shape of the state charts, how they characterize the states of the system, for example, or the transitions between them that we posit, how that affects the model outcomes. And then again, as time allows, we'll talk about statistical filtering, where we are over time estimating the state of our simulation model and updating our best estimate of it based on observed data coming in from the world. We're keeping the model in sync with what we observe from the world, recognizing that the data from the world is rarely enough to pin down exactly what's going on in the model, but it may make certain model interpretations, certain model states that we might be in less likely, and certain ones a lot more likely. This is the province of things like Kalman filtering and particle filtering and particle MCMC. And finally, we'll talk again, maybe in a final lecture, on dynamic decision-making, a very interesting topic of making decisions and setting strategy in the light of unfolding uncertainty concerning the world, where it's rarely enough to just decide on what's an optimal choice up front. Instead, we need adaptive decision making that adapts to the circumstance. Okay. So we're kicking off some coverage of this broad module. And I'd like now to transition to the first component of that module, which concerns stochastic processes in H-based models. And one thing I think I'll ask you to do, just to keep this a little bit more, to enliven the discussion, will be, and I seem to be splitting my attention between two different workspaces, is if you could open up the model within Canvas or the Fields LMS called multi-clinic. Well, if you look for that, it's enough. Multi-clinic SIS, hybrid saturation effects and lock inversion 3 is its full name. So if you open it up, what you'll see is a model where it has pretty familiar structure. So we have a state chart representing infection, including susceptible, latently infected people and exposed people who are posited further to be symptomatic, and people remain in this state until they're treated. And you may recall with this model, people's state of health, and particularly whether they're symptomatic enough, will influence whether they consider transiting for care. So if someone's exposed, if they're latently infected, they're infected but not yet infective, they won't yet seek care. But if they're in an infective and symptomatic state, in yonder state here, they will then transit to care with a certain chance per unit time. And when they arrive at care, they will enroll themselves in a clinic. We saw this in the hybrid modeling lecture, and get treated. You may remember. And once treated, they undergo either treatment failure or treatment success, and they depart the facility, which will bring them home. But whether it was successful treatment or not will determine whether or not they are cured of the infection. Okay. Now, what I'd like you to do, if we were to go run this model, I'm going to right click on baseline and I'm going to say run here, and I'm going to ask this thing to run. And you may or may not recall that this model, generally speaking, exhibited a certain kind of trajectory of outcomes. So it kind of kicked around for a while at low levels of infection, with sort of some people getting sick, some recovering, going in for treatment and securing that treatment within a timely fashion. But where, for a while it was comparatively low levels of infection often. And sometimes it would go through peaks and troughs. And there were times, you may or may not remember, where it went extinct. And the particulars of this trajectory during that initial phase were very much a matter of chance, a matter of happenstance. But eventually, in most runs, it started to go exponential at some point. It reached a tipping point, and it reached a lock-in state, from which we observed that it was actually harder to extract ourselves by far than it was to avoid it getting into that state. If we devoted just 2 clinics at the beginning, could reliably prevent it from getting in this adverse state. But once it reached this tipping point, the lock-in effect was pronounced in that it would require something like 6 or 7 clinics to extract our cells. Picking up the pieces is a lot more expensive here than preventing it. And I had made remarks about an ounce of prevention is worth a pound of cure, and that a stitch in time saves 9. But I'm going to dwell on another portion of this now. I note this transition here took about 11,000 time points. So we're going to run this again, and maybe we'll slow it down. And here we go. I'm going to run it again, and we will observe again it going through this initial phase of crenulations. But there we see it underwent the tipping point. And this time it took but perhaps around 2,500 days, maybe a little bit less, maybe a little bit more that it required, but not the 11,000 before. If we were to run it again, same settings, same exact assumptions within the model. Here we go. It's starting off. And again, it's hit that point around 2,500. And, we could run it again and again in a sort of brutal fashion. And we will find some variability. Here, this time about 5,000. And indeed, some of you may have discovered or recalled that in some of these runs, indeed, it may not take off at all. There are going to be some where it just dies out, just because of stochastics, through luck of the draw, dumb luck, happenstance, the initial people don't infect enough people, or they're treated, they elect to seek care before they infect many people, and infection never takes off. But what we've just seen is while there's variability, it's extraordinarily tedious to run it again and again. But that's what we need to do to find some sort of regularity, some sort of rhyme or reason, some sort of orderliness to it, isn't it? It's by running it again and again that we find certain patterns, that we may arrive at some distribution of how long it takes to reach that tipping point, or in what fractions of times it dies out such that it never reaches that tipping point. And if you go down here to the last experiment here called stochastic sensitivity, what you'll find is this experiment doing that job for you, as it were. So I am going to press this button here, and what I'll find is that it is running the model again and again, doing some about 100 times. It will be in total, and it's summarizing up across those, will soon be 100 different realizations, different stochastic stochastically driven runs, where I say stochastically driven because the assumption about the random number, the random number sequence will be different. Happenstance will be different, will happen differently. We see distributions of average clinic utilization over the model time frame, model time horizon. The average illness counts across the model time horizon, some upwards of 6. The mode being somewhere between 0 and 1.2. The mean being about 1.36. And here's the number of presentation counts on average, with most lying between 0 and 3, but some being upwards of 25 here. And I'm sure your results will look a wee bit different from mine, because even across those 100, there's some variability. So here we are running the model to arrive at firm findings. to arrive at an understanding of regularities in model finding, to bound our uncertainty about what happens with the model. We're eschewing running it by hand. Instead, we're using the power of the computer to run it in an ensemble. That's the name for it, an ensemble of realizations, each different in its happenstance alone. They're all making the same assumption about parameters. They're all making the same assumption about model structure. They differ only in chance events. But we can see those differences in chance events induce, by sheer luck, coupled with the model structure that makes it more or less sensitive to that luck, we can see real differences in model output within ranges. The clinic utilization seems to never go materially above 0.3 here. The average illness count, while it stretches upwards towards 8, it never seems to go beyond it. Average presentation count as most down towards the bottom, but there are some that are upwards of 24, certainly. So here we're running the model again and again and again in ways that differ, dear viewers, only in terms of their stochastic sequences, in terms of chance, as it were. So within models, there are commonly many factors that we seek to characterize stochastically as being influenced, as having randomness associated with them over time. Rainfall, changes in oil prices are maybe driven by more structural factors right now, for better or for worse. Economic growth, for periods that may sort of knock around. Other times it has more strong components. But even in some of these, as we've seen, there are stochastic effects of, actors of mercurial temperament who affect these things. And, bring this closer to home for health modeling, I will say, or for that matter, modeling in the commercial domain, individual behavior, the spread of word of mouth or spread of pathogen via transmission from one person to another, imitation of behavior, the severity of some infection, etc., may be considered for one model stochastic and not for another. We go to this model, we'll find stochastics. For example, how quickly someone seeks care is stochastic here. To who they expose near them. Exactly how many contacts per day they have. Who starts infected? Most people will start susceptible. A certain fraction will start infected. Where they are in the population may have some bit of impact. Whether or not a given visit to the clinic, a given episode of care seeking, is successful or not, is given by this probability of treatment success. So coin is flipped. This model has lots of elements of stochastic that for this model are treated aspects of individual behavior, aspects of contact, aspects of care delivery that are considered stochastic. It could be in some models that this is less the case, that for models of immune function, for example, we may seek to treat as more regular and perhaps even deterministic someone's response to a treatment or the severity of infection given exposure. There may be more structure added to the parties with whom they interact. That means it's less entirely variable who they expose. And in general, in a model, we may have some added structure, perhaps family structure represented, time spent with family, that may really shape those distributions to be a lot less spread than in a rough and ready model where we may assume that they can expose anyone. Or anyone around them at a time. Okay, so, within ABMs, and for that matter, within the discrete event simulations we saw last time, commonly, many of these things are stochastic. To whom you send a message, the duration of a procedure, the transition time between states, when events fire off, when that person has a bout of coughing that exposes others. And so there's going to be some variability, some variation in results from simulation to simulation. We've already opened this up. And a key tool in our toolbox, as we've noted, lies in this ability to run ensembles of models, ensembles of realizations, ensembles of runs, I should say. Running the model again and again and again and again to arrive at some distributions for particular outputs, and perhaps some deeper regularity, some properties of the system that are ensured across many, many runs. Perhaps we'll find that even though intervention A, I've commented on this before, perhaps intervention A yields one value that varies a lot, and intervention B yields a value that varies a lot with stochastics. But it may be that with those stochastics, the difference between them varies in a way such that intervention A always induces reliably more infection burden in the population than B. There's uncertainty about both, but the difference between them may be less uncertain. These are the sort of things we can explore with these ensembles of realizations with a simple model. And we will summarize stochastics, such as we saw, such as those empirical distributions we saw. Empirical in the sense we're summarizing data from the model. We are here in the sphere of, in the domain of stochastics, of statistics. We are looking at quartiles, of model results, not specific values anymore. And we may be interested in temporal sequences and regularities there, as well as, the differences that obtain at any one point. So let me make this point here. I've oft not made this point, but you could be forgiven when we showed this stochastic sensitivity and I sort of summarized the outcomes on these three with respect to three outcome measures. You could be forgiven for saying, well, okay, there's some regularities here with respect to these outcomes. This looks a bit bimodal. We have sort of high peak here, and then some peaks over here. This is kind of decreasing. And that's what this is showing is a bit of a cross-sectional depiction. at the final time, looking back, what was the average, so the average clinic utilization over the entire time horizon, or the average presentation count over the entire time horizon. It's actually a rather different question, and if I could press this point to bed, it's oft ignored or oft underappreciated. Let's run the baseline again. And we'll go back to this experiment just so that I can remind you of this. You may remember that we kind of knocked around for a while, and then, well, in this case, it could die out. So that's one sort of outcome that can occur. That's an important class of sort of outcomes. Here it died out again. So there's going to be some likely mode, some zero heavy or low heavy mode where it's died out a third time yet. It died out. Chance, now the fourth time it died out. This is an interesting contrast to earlier. But you'll notice here that if it doesn't die out, there's this sudden inflection, right, where it reaches high levels. And it notably differs. If you were to look at any one time, what is it? Say time 6,000, what would be the distribution of values there? You would probably find it quite bimodal. You'd find some peak in occurrence. If we kind of sliced many, many runs at this point, you would find some runs with very few infections or zero infections at this time. Zero infections left because it's died out. And then there'll be quite a few where it's up here. It'll be a tall mountain range up here, representing high chance it lies up here. But very little in between. And that reflects this mode of behavior that we're seeing. And if we were to run it again, we're likely going to see one of those two patterns. There we go. The exact timing of this will be different, won't it? And our parameters may make it, our assumptions may change the exact time in which this transition takes place. And evidently our stochastics influence the exact time under which that takes place. But the fact that it either dies out or it goes into this locked-in state, that's a real regularity here, not to be ignored, right? I mean, we could look at any one time and slice what it is and see a distribution, but we need to understand from a temporal standpoint, from the standpoint of understanding time behavior of the system in a given realization, it tends to cluster into one of two very distinct modes. It knocks around a bit and dies out, or it knocks around some, possibly for some longer time, it takes off and it goes to very, very high levels. And it locks into very, very high levels. What you don't see, and I would defy you to run it again and again, the baseline, what you will not see would be cases where it goes up to somewhere in between, where it goes up to, 600 and it just stays it. That's not in the nature of things. That's not in the nature of this system. It's drawn to these two different basins or two different equilibria, dying out or going up to a high level. Those are regularities over time. And when we're giving cross-sectional depictions, these kind of depictions of what value it is at a given time, we need to bear in mind there may be regularities of any one of runs, temporal regularities, that while they may differ in timing, have basic truths associated with them. Here, again, either dies out or it goes for a while and then it takes off. And we could try to quantify, we've never seen it before. Whatever the earliest was, 4,500 or what have you. We've never seen it after whatever it was, 11,500 or what have you. We could try to quantify that. But the fact that it falls into one of those two pretty dichotomous outcomes, there's really nothing between them, is very significant. I mean, that's a real property of the system. And let's not lose track. Let's not get caught up in the specifics of the distributions we see here so much that we lose track of that firm and interesting property and regularity. So, the orderliness of it is very striking, that it's basically dichotomous outcome here. This gives us some insights, but we are basically seeing a dichotomous outcome in terms of time behavior. Okay. So what we're exploring in characterizing this stochastic uncertainty, that these cases where same model, same structure, same assumptions about parameters, same recipe for the initial model state. Notice I'm picking my words carefully there. I don't necessarily mean it's the exact same people who start infected in every time. I don't even necessarily mean for some models that they're at the same position and there's the same network around them. We could normalize for that. We could be very prescriptive about our starting state, but most of the time we let that be drawn from stochastically unless we have some privileged knowledge. We want it to start from a exactly known state. Here, exactly who starts infected, as we noted, will differ from run to run, and who's placed in the same house as who, with whom, will be different. But other than that, all we're doing is we're running this model again and get with different assumptions about the stochastic sequence, the random numbers drawn. Happenstance. Happenstance is all we're looking at changing and seeing the regularities. Now, when we explore these, we have many lenses. I've shown one lens here, like this lens for stochastic sensitivity, where we examine in a histogram the outcomes. And we've seen that enough. I don't need to belabor this point. We see these histograms. And that's kind of summarizing one measure at the end. There are times where we will like to, for example, characterize the behavior over time in a way that is summarized across different realizations, across different runs, across different runs that differ only in their happenstance in the random number sequence. And this is the province of density plots, what are sometimes called histogram 2D plots here. And to show this, I'd like you to open up another model I've shared with you, SIRS crowding disparities V13 with stratified state space. So we had opened this up a week or two ago. So it's called SIRS crowding disparities V13. So SIRS. Okay, SIRS crowding disparities V16. I'll call it I'll do V16 because it's more recent, and I think that may be the one I posted. Don't sweat the number. Okay. So this one you may recall we spent a while discussing this at one point. We have susceptibles, infecteds, recovereds. We have a latent state where people can either spend significant time in that, or like in a case of primary TB, go quickly on to a case of active TB, without risk of spreading. The latent state may go on for TB for decades if it gets established. And you may remember, if we were to run this with a large population here, I was hoping to avoid running it with something too large so that we wouldn't take a while. You may remember this one where people have different incomes. The income dictates their position on the x-axis. The y position is stochastic. And the income distribution is skewed. It's log normal. And so you have more people in lower incomes than in higher. And people are wired up to others who lie within a certain, a given person. Two people, A and B, are connected if and only if they lie within a certain distance of each other. And therefore, you have a lot higher density of connections. You may remember this in terms of the different infection counts that it induces. This is actually connection counts. This is infection counts that it induces in different strata of socioeconomic status. What I want to stress for you here, though, what I'd like to emphasize here is actually another experiment. It's in this Monte Carlo baseline here. Okay. I'm going to run this, and what we're going to see here is one of these density plots. So I am running this model across many particular runs of the model. And unfortunately, it's a bit hard to see here. I'm going to go and just open this up. We will see that it's running at 100 times. Unfortunately, in mine, it's just quite faint. But we have basically a band down here. So this is time, I should say. This is time, and this is number of people infected, or the incident case count, the number of new people getting infected at that time. And what we have here is a density plot. So it's darker, and it obviously doesn't get too dark here, but it's darker at a point where you have a lot of different runs falling there. So in a lot of runs, the number of people getting newly infected within the last bit of time, at time, say day 200, lies in this region between 0 and between 2 and 4, it looks like, or 0 and 2 here. There's also quite a few, and I don't know if you could see them, which lie somewhere between, it looks like 54 and 56. There's 1% of the runs fall within that range, and then up to about 94 and 96. So there's kind of a range of hills or mountains here. This is bimodal. And then there's a range down here. And I apologize that it's so faint. I think it's because everything starts here. So this is really dark. And it kind of saturates out everything else. unfortunately. Were I more artful, I could have gone in and excluded that first one. I'm going to go back to this. I'm tempted to go and yeah, I think I'll avoid tempting fate, and I'll just go back here. Okay. Okay. So this is a 2D sensitivity analysis that provides a summary in a histogram 2D object of many, many runs. Perhaps what I'll do, just to make it a little bit more obvious, I'm going to open up help, go to example models here. We are going to go in example models down to SAR agent-based calibration. It's this one. And you'll notice that there's a Monte Carlo 2D histogram here. Okay. This one is less saturated. And so I think this running Monte Carlo 2D histogram. So this cross many Sorry, folks. Somehow I got disconnected there. I'm going to go back to sharing my screen. So what I was describing was a 2D histogram, a little bit less obnoxiously covered. So here we are characterizing called 2D histogram because we have bins in the direction of time. So this is time. We have bins of time between like 40 and 42.5, and between 42.5 and 45. So these are evidently of size 2.5 going along this direction, X to Y. You could think of these little rectangles as a bin, and it's counting the number that fall in there. In the Y direction, it's evidently of size. So this is 0 to 200. You notice the scale of this is rather different. So 0 to 200, 200 to 400, 400 to 600, etc. And so there's going to be a number here of runs in which the number of infected people between time 40 and 42.5, you could see those numbers shown on my screen. Between time 40 and 42.5, some number of runs at that time had a number of infected people that fell between 0 and 200. Do you see the 0 and 200 there? And what fraction of all runs had representation in that bin, fell in that bin, had the number of infected people in that bin? Well, it was about 11% of runs. That's why it said 11. Okay, now it's down to excuse me, now it's 10.8% of runs fell there. By contrast, up here, in that same time interval, 40 to 42.5, 35.8% of the runs, 35.4, 0.5, 0.6, I won't keep up with it, fell between 1,400 and 1,600 number of infected people at that time. Mm-hmm. 25.8 of them fell here. So here we do have some representation, but it's about roughly a bit less than 10%. And probably by extension, about 90% of the runs fell here. Between here, nada. Basically 0% fell within that range. This is capturing one of these regularities. Either it dies off early and stays low, or it goes up and comes down, and very few of them come down in time to contribute to this. So I would wager that these 9.5 or 10% along here are all ones that probably just did not take off and then stayed at very, very low levels all throughout subsequently. By this time, by contrast, 99.5% of runs have come down to this level, or at this level then. There's going to be about 10% of them that stayed low. Mm-hmm. But the remaining 90%, the vast majority of them went up, came down, and were down by this time. By the time you get to 100 times 100, essentially all runs fall there. Regardless of whether they took off earlier or not, that's where they are now. So let us reflect on this, shall we not? There's variability here. There are chance events. There's happenstance. Some runs take off, some don't. But there's boundedness in that. There's enough structure here that there are really firm regularities on which we can hold in these model results. By time 100, essentially all have converged here. By contrast, by time 20, there's this real divergence with about 10% down here, 9.5%, and the rest up here. At the initial time, virtually all are down here. And though there's differences in exactly when they come down to different levels, there's essentially nothing above a certain point here. Well, okay, so there's maybe there's one up here, 0.5%. But there's really bounded uncertainty. Is there uncertainty? Absolutely. Is that uncertainty all over the map? Absolutely not. It is bounded. It has shape. It has form to it. There are certain properties which hold with great confidence because of the dynamics involved. And by exploring model variability across many runs, and tomorrow we'll see how to do this in lab, set up some of these experiments, we can test these properties which hold across many runs, not by brutally, manually rerunning it and rerunning it and rerunning it, by creating experiments which run it automatically many times with the same assumptions and summarize the results using things like histograms that summarize results across the entire runs for run after run after run, or techniques like these 2D histograms. And it will behoove us to also remember these regularities that occur over time with a given run, like it's going to take off, it's just a matter of when. Or either it takes off at some variable time within a range, or it dies out. Those are strong regulators. So, well, this will be mostly the province of tomorrow's lab. I'll just note that there's within this particular package, AnyLogic, there's a hierarchy of sorts of distinctions made for different, for running these sort of experiments, and these hold over for other things like calibrations as well. So we're going to have an experiment during most of the class, sessions as class. I've hewn to the linguistic choice to abbreviate these, call these scenarios, and one can be forgiven for saying, but they're termed experiments in AnyLogic, and hence the X. And within each experiment, there may be many, I'd say, simulations here. It's really a iteration. It is sometimes called a simulation, but where we run it again and again and again, stochastically, maybe with a certain set of parameter values, and we get a mean value across all of them. And then there's a replication, which is one run of the model. Now, if we're just running the model with the same parameter assumptions, we don't distinguish too much between the latter two of these. But I will show you that within each run here, we can go set the so-called replications. And replications allow for a given set of assumptions, like this one here, where we're drawing for a given this value from this range, and then we'll run it 10 times for that, and maybe we'll get some results for those 10, some average results. So we might have an experiment which is going to run this again and again and draw different values here, and for each of those, for a given value drawn from this random distribution, I will run this 10 times, and I will summarize the results. Here we have an experiment. That's this overall thing. A simulation or iteration where I'm drawing, I have the same parameter values for that whole block, iteration or simulation. And then within that, I'll run many replications, which differ only by stochastics, what I would call realizations of the model with the same parameter values. Right. Okay. And I give some guidance for those seeking to learn how to apply this, for how you can set up a run to have the results summarized in these sort of 2D histograms, or for that matter, in regular histograms. And tomorrow, I hope to explore that with you in tomorrow's lab session. Okay. It turns out that there's a set of options with these 2D histograms. We can elect it to summarize the data in different ways, showing envelopes of values around the median, or showing bins, the sort of empirical histogram. And I provide some comments here in case you're interested in understanding some of the differences between these. They're each useful for different purposes. I tend to, for the most part, look at bins, so tend to look at empirical quantiles that fall within certain ranges, and less so use the envelopes. Some guidance here if you are interested in characterizing things with envelopes around the median. You can specify the successive contours further out. So here I have a contour around the median in which 25% of runs fall within a window versus 50%, that's 0.5, versus 75%. And I want to show those envelopes over the course of the simulation. And this is going to show what fraction of runs at that time fell within those successive envelopes. So 25% would show it's a little bit like a box plot, the sort of range at that time, the range within which 25% of runs fell, 50% or 75%. And you could have it 95%. 95% of the time that they fell within a certain. Right. Okay. I think that's all we have time for today. On Thursday, tomorrow, we will have a lab and we'll be exploring some of these stochastics. My plan has been tentatively to also explore a bit of hybrid modeling tomorrow as well. I'm going to see if we can square that circle so we could do both. I've got to think about that some. And Friday, we'll be continuing on to discuss parameter sensitivity analysis, both one-way, multi-way, with Monte Carlo, as well as parameter sweeps. And how we can examine how model behavior differs, sometimes a little, sometimes a lot, as we vary parameters in different ranges. And we could see the nonlinear character of model can induce pronounced differences in results for certain ranges of parameters, even though it may be less sensitive for other ranges of the same parameters. That's for Friday. Okay. I will stop now